Alright guys, today we're looking at loads of derivatives. I'm not going to do an intro, I'm just going to get straight into it because I've got no time to spare. So, let's say f of x equals x to the n. That can be any polynomial, that's what we'll start with. Any polynomial, x squared, x cubed, x to the 4, anything you want. I thought about that way too much, x to the 4. So, we're going to find its derivative, which is written as x prime of f prime of x. And we're going to find what that is. We'll start by using first principles, and we're going to use that a lot here in this video. If you don't know what first principles are, I recommend go to my pilot video where I really go into depth about what first principle is and explain how it works. But essentially, we're going to take the limit as some delta x called h approaches 0, and we'll find our delta y, which is f of x plus h minus f of x. Which makes sense. We've got a y coordinate at x and a y coordinate at x plus h, so we'll just do f of x and f of x, essentially. But I'm going to rub that out so I've got more space to deal with, because we can just substitute that straight into the equation. F of x plus h is going to be x plus h to the n, and likewise minus f of x will just be minus x to the n. And then we put that all over our delta x, which is h. Now we can't just substitute h in immediately, otherwise we'll get a massive problem. So instead, we will work our way around it. For example, this x plus h part here, I can write all the brackets for that, yeah? Just a load of factors in brackets that goes on n amount of times, right? Now, let me just grab a different colour. If I do x times x times x times x so on, all n times, I'm going to get x to the n. That's my first term, okay? Now, I'm going to do h times x times x times all those other x's. So I'm going to get plus h, and then instead of x to the n, we've got x to the n minus 1, because I've just added one less x than before. Big issue is though, I could use this h or any other h in the whole series. So to account for that, I'm going to take in every single possibility. How many of those possibilities are there? N of them. So I do n times this part here. And that's all you really need to worry about for now. There's a much better way to do all of this. It's called the binomial theorem, but I don't want to have to go and explain that for now, so I'm just going to leave it at that and say the rest of the terms are h squared or higher. There's a better way to write this. It's O of h squared. Basically means every term onwards is h squared or higher, which makes sense because I could use 2 h's times the rest of the x's or whatever I want, you know? So let's put that back into our equation then. That means that, there we go, that this limit as h approaches 0 is going to be this part, x to the n plus n times h to the x to the n minus 1, and then plus everything else with h squared minus x to the n, like so. Hopefully you can see that. So now we're going to put that over h again, and let's see what we can cancel, right? We can cancel this x to the n, those minus out. And then look at that, we've got h and a h, because all these have h's in them, and a h, which we can cross out. So this limit is actually equal to n times, remove the h, so n times x to the n minus 1. And then everything here, well, it used to be everything h squared and higher. Now it's going to be everything h and higher, because h squared goes down to h when divided. Hopefully that makes sense. So we'll write O of h. But the thing is, all of those terms as h goes to 0 are just going to evaluate to 0 as well. If you look at over here, if we put 0 into this, then all of this would just evaluate to 0 anyway, and so would every other term onwards, because it's being multiplied by h, or multiplied by 0. So therefore, we say that our first derivative of x to the n is going to be this part here, which is n times x to the n minus 1. And this is what we call the power rule. Well, basically, this, you bring down the power, so it's n times by x, and then subtract 1 from the power. This is the most basic differentiation you'll really ever have to do with polynomials. Alright, moving on to our first derivative, we're now going to look at sine of x. And we are going to have to use 3 facts to do it, and I will prove these in future videos. Our first fact is that sine of a plus b is sine a cosine b plus sine b cosine a. Got a nice chiasmatic pattern to it. Next, we're going to use the limit of theta going to 0 of sine theta over theta equals 1, and likewise, the limit as theta goes to 0 of cosine theta minus 1 all over theta equals 0. That makes no sense to just about anyone right now unless you know the explanation, and I will do one in a future video, I promise. But for now, let's just focus on the derivative and then we can look at why this stuff works. So, first of all, we're just going to simplify this down using what we've got up here. X is A, H is B, and so we are going to write the limit as H approaches 0 of sine X cosine H plus, in this case it's plus, sine H cosine X, and then all minus sine X, and then all over H. Cool. Now let's split this fraction up a little bit, just to make it easier for us to deal with. First of all, notice how we've got a sine X and a sine X there, right? We can factor those out into one term. So sine X, and then it's cosine H minus 1 now. Cosine H minus 1. And then that is over H. Now we're going to add our cosine X, cosine X, times by sine of H over H, like so. So now we've kind of grouped up the H's and the X's. The reason why I'm going to do that is I'm going to say 2 things. First of all, when you've got 2 things added in a limit, you can just apply the limit to the 2 things, like so. So we've got limit of this and the limit of that. And now, as you'll see, we've got something that doesn't involve H and something that doesn't involve H, which we can just take outside of the limit so that we know what to focus on. So sine of X is times by the limit as H approaches 0 of this thing. But hang on a minute, look at this limit for a second. It's what we've got over here of cosine H minus 1 over H. That's just the H has been replaced by theta, and we know that this is going to evaluate to 0. And if we have sine X times 0, then that is also just going to equal 0. Okay, that's useful. Now plus the second limit, well, times cosine X obviously, and then the limit as H goes to 0 of sine H over H, which I'm sure you'll recognize just the same. If you replace H with theta, you get what's up here, and that equals 1. So that means cosine X times by 1 is just going to give you cosine X. And so our f prime of X, our first derivative, is just cosine of X. Nice. Alright, so we've just done polynomials, we've just done sine, now we're going to look at the cousin of sine, appropriately named cosine. So, finding the derivative of cosine is not going to be easy unless we've got these 3 tips here as well. So just like last time, I will show these in another video, but for now, let's just look at them. We've got the same 2 things here, these 2 limits, which we used last time, and a new one. Cosine A plus or minus B is equal to cosine A times cosine B, minus plus, that just means whatever we use here, we do the opposite there, minus plus sine A, sine B. I think that's pretty easy to remember. Cosine, cosine, sine, sine, AB, AB. In this case, we've got a plus, so we can write this limit as H approaches 0 of cosine X times by cosine H, that's how we use that formula, minus sine X sine H. I hope you could understand how we got that. And then of course we minus cosine X. Can't write. Put it all over H. Now, similar to last time, we're going to take things out and we're going to separate them from the limit and yada 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 just to simplify this down. For example, I see a cosine X and a minus cosine X, and they're both times by something in some sense. So we're going to write cosine X on the outside of this limit, because remember, it's not affected by the limit, just like we did last time with sine of x. So times by the limit, as h goes to 0, of cosine h, and then that's a minus 1 there, because if you times them out, that's what you get, and then we put it all over that fraction h. Now minus, again, we can take out the sine x, because it doesn't really affect us in any way, and then times by the limit again, of this time is going to be sine h over h. Cool. And once again, we see our two limits show up. This one we know is going to evaluate to 0, so let me just write that there, equals 0. And then this one, well, we know this is going to evaluate to 1, and we've got a minus sine x, which means that the derivative of cosine x equals minus sine of x. Now normally you'd expect me to find the derivative of minus sine of x, but actually we just did that. It's just the negative of the derivative of sine, assuming that's meant to be sine. And so we know that that has to be equal to negative cosine x. And this produces a really cool pattern. Let me show you that. So the really cool pattern here is that if I take sine of x and I differentiate it, I'm going to get cosine x. We just saw that. And we just saw as well that if I differentiate cosine of x, I get negative sine of x. Now, negative sine of x is just sine of x, but with a minus 1 attached to it. So if I differentiate that, I'm just going to get cosine x, but then add in the minus 1 and you get negative cosine x. And finally, if you differentiate that, well, cosine x gave us negative sine of x. So if you do that, you get negative sine of x, but negative and negative is just a positive. So we go right back to where we started. And this is the wonderful clock I wanted to show you that you get with sine and cosine. I know that MathsJan likes to use it a lot to differentiate sine and cosine, and it's a really useful method. Just remember which way to go around the clock, and you can't go wrong. Okay, moving on to e to the x. Okay, for our penultimate derivative today, we've now got e to the x. And we'll use one fact for this, that e to the x equals 1 plus x squared over 2 plus x cubed over 6, and so on with higher terms of x. And you'll see why that is in a future video which I'll upload, explaining how e works, why it's special, blah blah blah. And I think you'll really like this one. This is really interesting. Oh, sorry, I forgot the limit. The limit as h approaches 0. Do not forget that, otherwise this all makes no sense. Okay, so we take the limit again, just to make sure we don't forget. And we can simplify this part, e to the x plus h, by saying it's equal to e to the x times by e to the h. That's just index laws. And then of course minus e to the x all over h. And you can see now that we've got another thing that we can factor out. And so we're going to do that again. We're going to do the limit as h approaches 0 of e to the x times by e to the h minus 1 all over h. But remember, we can just take this out of the limit because it's not going to affect it at all. There's nothing in terms of h there, so e to the x and then times by this limit. Boom. Okay, and now we need to figure out what this part is. Well, this is where it's pretty useful to use this definition right here. You'll see why. E to the x times by the limit as h goes to 0 of 1 plus, in this case not x but h, we're substituting h into it. So 1 plus h squared over 2, and you know what, I'm lazy so I think we'll leave it there, and then minus 1. I'll just specify that to 1 so you can see, and then all over h. Now, here's what's special. That 1 and that 1 cancel out, right? But now look at that. We've got a h and a load of other h's divided by the h. Cancel them out, just like we've been doing the whole time. And so what we're left with is e to the x times by the limit as h, goes to 0. And then we've got, well, that goes to a 1. That goes to, what is this? H over 2. Then that becomes something else that I don't really need to care about. And As you can tell, as h goes to 0, this is going to go to 0, this is going to go to 0, everything else goes to 0. We don't need to care about that. All we need to care about is this 1. And so what we've got here is e to the x times by 1. I'll change that actually. There, times by 1. But anything times by 1, it doesn't matter because it's just the same thing. And so, as you can see, the derivative of e to the x is, oddly enough, e to the x, which is, I think, such a cool fact about calculus and about all this kind of stuff. And it's why I love e to the x, because it's the easiest, e for easiest derivative you'll ever have to do. I'll do a little smiley face. Right, so I did call e to the x our penultimate derivative, and here's why. Because we're going to look at the natural log, but what is a natural log? Well, first of all, it's written as ln, if you want to call it that. And I've written a note here that ln x equals a implies that e to the a equals x. That's the definition of the natural log. It's basically saying if I've got e to some power that gives me a value x, or if x equals e to some power, then if I do the natural log of x, I get what that power is. And it's really useful because it allows us to do stuff like what I'm about to show you. Okay, so where do we start this time? You'd think first principles, but actually no. This time we're just going to use some logic and work through it step by step because we don't actually need first principles for this derivative. First of all, we'll just put f of x as the power of e, and we'll do the same on the other side. Ln x is the power of e. So we get e to the f of x equals e to the ln x. You may be wondering, why would you do that? That's just really weird. It looks more complicated than when we began. But actually, what's special about this is that these two are inverses, as I showed up here. So these are inverses, so we can cancel them out, which gives us x. And now this equals e to the f of x. Okay. So where do we go now? Well, what we can do is we can now differentiate both sides. That's what this symbol means. It means differentiate. Bit tight there, but whatever. If I differentiate x to the 1, we talked about that earlier. That's going to be 1 times x to the 1 minus 1, which is 0, but that's just going to be 1. Okay, so that's a 1. And as a derivative of e to the f of x, well, we talked about this. If we've got e to the f of x, if we've got, we talked about this. If we've got e to the x, that derivative is just going to be e to the x. But the special thing here is we've got f of x instead. I won't go into depth too much why this works, but all you have to do is, because it's f of x, not x, you just take the derivative of this as well and bring it down. We'll go over that more. It's called the chain rule, okay? And there will be a video on it. So we bring down the derivative of this, which is f prime of x, and we times it by e to the f of x, like that. And that's the derivative, and that equals 1. Okay, cool. Now, if we want to find f prime of x, we'll say f prime of x equals, we divide it by it, 1 over e to the f of x. But hang on a second, we said that e to the f of x is just x. And so, the first derivative of ln x equals 1 over x, or x to the minus 1. And as you can see, x to the minus 1 is a polynomial, which we can then use this idea to differentiate further. And there we go. The reason I've done all of that today is because I want to answer a bigger question in time. What are the conic sections and why are they useful? Now, conic sections, if you don't know, is a topic that, a topic that comes up in 2 chapters of Further Pure in Edexcel A-Level Further Maths. Now, I've already started the first video by doing the differentiation of certain functions. Now, next video, we're going to look at the rules and methods in differentiation, like the chain rule, the product rule, and so on, and then we'll derive those rules. Then we'll look at parametric equations and recap some graphs and shapes that we already know. Finally, we'll look at what the conic sections are, their properties, and one particular one, eccentricity. Once we've done all of that, we can then look at why they're useful and apply differentiation to it. So I hope you're looking forward to this as much as I am, because I'm really hyped to get going with this. Peace out.